Photons have to be literally everywhere all the time, even in a dark room. If I can see, then there's photons hitting my eyeballs.
Muhammad Ali said it best.
I'm pretty. That's right, Howard. I'm so fast, I turn off the lights and I'm in bed before the room get dark.
That's the one I'm talking about.
Oh, really? Yeah.
This is Startalk. Neil deGrasse Tyson, your personal astrophysicist. Chuck Nice over here.
What's up?
All
How
right,
are you, Neil?
We're going to do another Cosmic Query.
Grab a bag.
That's all we're doing lately, are grab bags.
It's a fan favorite, man.
It's like you close your eye, reach in the bin,
That's
and
right.
pull it out.
Pull out a snake.
You know, I actually have a black hole bag over there. Did I ever show you that?
Wait, I thought it was the black hole lunchbox.
Can I only have one black hole thing? Is this what you're
I know. Who
think?
am I talking
I'm going to show you. Wait, hang on. Okay.
You might have shown me this a long time ago. This is a black hole bag. Oh, Lord, Lord Jesus. What the hell?
It's a
What
okay.
the?
Okay.
I love it. And then there's the eyes.
Oh, no, I forgot what I put in here.
Okay.
I put a hole in here.
You put a hole in the hole.
Yes. What a place to put a hole.
Doesn't.
Don't you remember my
Oh,
hole?
I remember the hole.
You
now.
remember the hole? This is a hole.
We did that whole thing where we cut
This
the
is a
square,
hole.
and then you could walk
What
through
I said
it.
was like, here's a sheet of paper. I'm going to cut a hole in this sheet of paper that you can walk through.
That's right.
And you said no.
And I said, no, you can't.
No, you can't.
But you did.
And I still in
That's
here.
a very cool thing.
Yeah. Chuck, what you got for me?
All right.
A grab bag.
This is the grab bag, and I will pull it out of this black hole made by Apple computers.
Galactic Gumbo.
The Galactic Gumbo. That's right. They never shown them got my dad didn't do. This is Dalton. Hey, Dr. Tyson, Lord Nice, greetings from Huntsville, Alabama. I was watching
Huntsville, Rocket City.
Rocket City.
Which Trump officially named. Well, by the way, it was always named Rocket City.
Right.
And then Trump decided to.
I'm going to officially name it Rocket City, not to be confused with Little Rocket Man.
That's like coming to New York and saying, I'm going to rename New York the Big Apple.
Which he would do that, by the way. Anyway, that's so funny. Greetings from Huntsville, Alabama. I was watching an old explainer on absolute zero and why it's impossible to reach it. If it is impossible by quantum physics to have a particle become completely stationary, then would it not be possible to extract infinite energy from it in the form of heat? In doing so, violating the first and second laws of thermodynamics. It seems a bit paradoxical to never be able to reach absolute zero, since you seemingly can always have something colder. But that, I don't know why you would say you seemingly could have something colder.
No, he's what this is, Dalton? He's merging a classical brain with a quantum brain. Okay.
Right.
In terms of his interest in answering the question.
Right.
So just let me talk you through this.
All right. Talk you off the ledge, Dalton. It's going to be okay.
Talk you off the absolute zero ledge.
Yeah.
All right. So let me just remind people that there's no such thing as cold.
Right.
You can't like put cold in something.
That's where I was going when I said it's.
If you could do that.
Right.
Then you can make something like infinitely cold.
Yes.
Just add more cold.
Add more cold.
So what we sense as cold is just the absence of heat.
Right.
So you start pulling heat out.
Right.
This is what your refrigerator does.
Right.
It pulls heat out of your food.
Right.
You don't think of it that way.
Right.
You put in something that's room temperature, it takes the heat out.
Right.
If you take heat out of something, what happens to its temperature?
It goes down.
And you take it out, where does that heat go?
It's got to go somewhere.
It's got to go somewhere. Sure. You ever go around back of a refrigerator?
Goes out the back of your refrigerator.
You ever go around back?
Hot as hell back there.
You ever go around back?
Yeah,
those coils are dissipating coils to send out the heat.
Send out the heat.
It not only radiates the heat, but it's in touch with air, so the air will conduct heat away as well.
Right.
Okay. By the way, this is a major issue with spacecraft.
Okay.
Because if you're in space and you have machines that generate heat,
right?
How do you get rid of the heat? You got to dump the heat somehow.
Okay.
So you can't just have, you can have radiators, yes, but each radiator has to be pointing away into space. Mm-hmm. They can't point to each other. You can't have a battery of radiators, right? Not a literal battery, but like
an array, an alignment,
an array of radiators that are like, if they point to each other, nothing. Yeah, it just feeds each other the same heat.
It's like I'll heat you, you heat me.
Exactly. So they all have to face space, but it doesn't have the benefit of air whisking away the heat. It can only radiate it away. Whereas on Earth, you can release heat both ways.
Okay.
It can radiate away, and you can convect air around it, and it just takes it away.
Right.
Very efficient.
Right.
When you have a medium such as an atmosphere to do that. Right. All right. So
cool breeze.
The cool breeze will cool you down faster than just you radiating your whole heat. Okay.
Right.
It's slightly different. The cool breeze is forcing your sweat to evaporate.
Right.
And the evaporation takes energy out of you. But so let's get back to the absolute zero. So I keep taking heat out, and the temperature gets lower and lower and lower. You reach a point where quantum phenomena dominates, and you can no longer use classical reasoning. This, by the way, Dalton's not alone in this intersection, this troubled paradoxical intersection between classical physics and what we call modern physics.
Okay.
So you get down there, and you try to take more heat out, and you can't because and by the way, taking heat out means that particles are moving slower and slower.
Right.
Okay. The heat is vibrational energy typically. Okay. So you take that out, and there's a regime where the quantum fluctuations prevent it from ever stopping its motion. All right.
Okay.
So you're saying, that means there's energy there.
Right.
Let me pull that energy out.
Let me utilize that energy.
I think I'd have to confirm this with our cosmology trio.
Brian and Jana.
Brian Cox, Brian Green, and Brian Cox, of course, is in the UK.
Right.
But he comes through, and he's a good friend.
And then sometimes Sean.
Sean Carroll.
Right.
Oh, yeah, he's a good guy, too. When we speak of 0-point energy of the vacuum of space,
right,
I think that's what they're referring to. The energy below which you cannot go. Okay. Because it's 0 point, but it's not really zero.
Right.
But if you try to get to zero, that's what you're stuck with. And that's quantum fluctuations. And I don't think you can extract energy out of that lowest energy fluctuation, because it needs to take energy out, you need a lower energy state to land in.
Right.
And you can't.
Right. Because that's it.
Who's that guest we had in another show? A biologist who said, the universe is just electrons looking for a place to rest.
That's it. Yeah, that was Bitul.
Bitul. Yes, Bitul from University of Madison, Wisconsin.
Yes.
Bitul. The universe, everything that happens in the universe is an electron
looking for a place to rest.
Looking to hang its hat.
Yeah.
And so...
Honey, I'm home.
A hard day in the circuit. But people imagine that you could tap this 0-point energy and make like rockets out of it and travel through space. And I don't have problems people imagining that. It doesn't seem likely to me, though, based on what we know of the behavior of quantum physics.
Gotcha.
So there you have it.
All right, Dalton, way to go, brother. Mm-hmm. Hope that keeps you from,
keep you on the ledge.
From jumping off the ledge. All right, this is Rachel Ambrose. Rachel says, Rachel here from Austin, Texas. Photons have to be literally everywhere all the time, even in a dark room. If I can see, then there's photons hitting my eyeballs. I feel like people don't talk about this enough. They are filling every inch of space all the time. They're everywhere. Furthermore, somehow photons from the Big Bang are still here right now in the form of cosmic microwave background radiation. Neil, can you please speak to this?
Yes. Muhammad Ali said it best. Mm-hmm. Okay.
I'm pretty. That's right, Howard. Look at me. I'm pretty, Howard.
Well, Howard Cosell.
Howard Cosell. I'm so fast. I'm so fast. I turn off the lights and I'm in bed before the room get dark.
That's the one I'm talking about.
Oh, really? Yeah.
That's the one I'm talking about.
Yeah.
So he knows that photons have to go,
Right.
Well, he's thinking that dark is penetrating the room,
right,
but light is exiting the room.
Right.
When you turn off the light. The light gets absorbed and it's gone. Your eyes are not the ultimate arbiter of whether there are photons in the room.
Right.
Because your eyes only see red, orange, yellow, green, blue, violet.
Roy G. Biv.
Yeah. Oh, sorry, indigo, violet.
Indigo, violet.
If you got to get the Biv going there.
Yeah.
Isaac Newton put in the eye.
Did he?
Yeah. Because he's mystically fascinated by the number 7. A spectrum can't have 6 colors.
It can't have 6 colors.
You got to,
yeah. What kind of animals do have 6 colors?
What kind of stupid universe would that be?
Throw some indigo in there. Yeah.
No, but if he got deeply religious, he could say, well, the universe was created in 6 days.
Right.
You know,
there you go.
It's not 7 days, 6 days.
Yeah, that's
people forget. It was 6 days.
6 days. 7th day he rested.
He rested.
Which I'm just saying, what kind of God is this?
He needs to take a break.
Like, me is so damn hard. Oh, me is hard.
Oh, me. Oh, my me.
Oh, my me. It's so hard to make a universe. I need a rest. Oh, Lord, I can't do no more. Did I say Lord? Who am I talking to? Oh, Lord, me is hot in this. Oh, I'm so tired. Anyway. Okay. But
now I forgot what we were talking about.
Photons everywhere.
Photons. Right. So anything that is at any temperature at all,
right,
is radiating photons.
There you go. That's what I was going to say. Because if you're a predator, you see photons all the time.
You mean the movie character?
Yeah, the monster with the dreadlocks.
Yeah, because he had dreads.
Yeah,
he had dreadlocks.
Yeah.
So Predator,
I didn't appreciate that.
Could see in infrared.
Right.
Okay.
Exactly.
Now, you know what's interesting?
Go ahead.
Just a little fact.
Right.
I think about movies all the time.
Okay.
So that was only cool because the infrared was the shadowy shape.
Right.
That means he has low resolution infrared cameras.
Right. Yeah.
We got better cameras than that today.
We do.
High resolution, you see the full person there. Depending on your temperature, it will determine what kind of light you're predominantly going to emit.
Right.
So at our temperature, we emit primarily infrared, so we'll show up in infrared. We reflect visible light.
Right.
But we emit
infrared.
Your walls are room temperature, so they'll emit a little less infrared because they're not as warm as we are.
All right.
You keep dropping the temperature. What's on the other side of infrared? Microwaves.
Okay.
And then radio waves. So the colder it is, the further down the spectrum it shifts. So that when you're only 3 degrees Kelvin, 3 degrees above absolute, you're giving off microwaves.
That's it.
And that's the cosmic microwave background.
Space, right.
That's it.
Cosmic microwave background.
So yeah, and it could be dark for you, no problem. Not many people have been in complete, total darkness in their life.
True.
Do you know how to get it?
I'm going to say blindfold and
that can help.
And then bury yourself alive.
Okay. I was thinking of other ways for that.
Okay.
But if you go spelunking.
Oh, you mean to a cave? That's way.
You go deep into a cave, make a few turns.
So there's no light getting in at all.
Turn off your flashlight.
Right.
You cannot see
anything.
Anything.
Yeah. See, now, and no disrespect to anybody, but that's some white people stuff.
No black man ever died.
You will never find a black man dead in a cave with no light at all. No. First of all, I'm not going in there because even with a flashlight, it'd be like, where'd Chuck go? I'm not doing it. I'm not doing it. Okay? These are jokes. Don't write. Don't write. All right, I'm going to stop. Let's move on. All right. So there you go. Rachel.
I like the Muhammad. Give me the Muhammad Ali commenting.
That's right. I'm so fast. I'll turn off the light. I'm in the bed before the room get dark.
Yeah, that's good. Yeah. That's a really good one. What would you do if an alien actually showed up? Would you shake its hand or run? Does it even have a hand to shake? In my latest book, Take Me to Your Leader, I explore not only how they might have gotten here, but what they might want and how you should respond. Because the real question is not, are we alone? It's, are we ready? By the way, I also narrated Take Me to Your Leader, and I'm duly informed that you can get a copy of that book or the audiobook now, wherever books are sold. You should probably get the book sooner rather than later. You don't want to have a first alien encounter and not be ready for it. I'm just saying.
This is Max Wilburn, who says, hey, Chuck, hey, Neil, this is Maxwell from Lexington, Kentucky.
Ooh.
And I know Neil thinks very highly of Newton, as he has accomplished so much, but recently I learned about Newton's law of cooling. Although it's not as fundamental and such a stepping stone for the world of physics, I just find it insane that as a side quest, he did that. What a badass. What are your thoughts?
I did not know about his law of cooling. I don't know about the law.
I think his law of cooling was, don't you love my hair? Look how cool it is.
But I think that was a wig he was wearing.
Oh, no.
I was so distraught upon learning this.
Really?
Yes.
So his hair notwithstanding, do you have anything to say about the law of cooling?
So I didn't know he came up with that, but it is a well-known means of calculating the rate of temperature change in physics class.
Okay.
Yeah. So the way you do it is you have two materials at different temperatures.
All right.
Okay. And you bring them in contact in some way, either physically, so that atoms are touching each other, or have air molecules bouncing back and forth, or they're radiatively connected. Connect them in some way.
Okay.
Okay. And then you measure the rate at which the temperature changes so that they reach equilibrium to each other.
Cool.
Okay?
Right.
So it's not just that sorry. One of them might have a continual source of energy going in. Mm-hmm. So then the cool thing comes up to its temperature. You see what I'm saying? But if they're two isolated objects at different temperatures, they will meet in the middle somewhere.
Right.
At a temperature lower than the high one and higher than the low one.
Gotcha.
All right. So you can calculate the rate at which the temperature changes.
Oh, okay.
Okay? And deduce, as Isaac Newton apparently did. I own everything that man's ever written, and I've got to go dig that up.
You got to go dig up the law of cooling.
That must be a chapter I missed.
Yeah.
Okay? So what it states is the bigger the temperature difference, the faster the rate of change of temperature will be.
Okay.
Which kind of makes sense. It just kind of makes sense.
Yeah, absolutely.
Yes.
Right.
And if you do some measurements of that, you can actually represent it with an equation.
Okay.
And you make a prediction.
Right.
This is the temperature difference. They'll be the same temperature in 10 minutes.
Right.
Or, by the way, this is happening every day. You get a glass of water, you put ice in it.
Right.
Eventually,
it's going to be water.
The ice will melt. And then you have water that's cold, but it's still air temperature out here.
That's right.
Eventually that comes up.
And that comes up. That was an assignment in physics class when I was in 8th grade. And what we had to do was plot the melting of the ice in a graph to see whether or not it was linear. And it was.
Yeah, that would be a cooling curve.
Yeah, that's a cooling curve.
It's gaining heat from the outside.
Exactly. Yeah.
So
there you go. Look at that. See, people, these are the things you can think of when you are not busy thinking about sex, like Isaac Newton. This is what happens. You become a genius because you're just like, well, I ain't having sex, so I might as well think about how do things melt.
Yeah, he never married, had no children, had no known intimate relationships. And so we're pretty sure when he came up with his law of gravitation and motion and calculus,
right,
that he was a virgin.
Right. There you go, babe. That's it. Like a prize fighter. You know what I mean? You know what they say? You got to stay hungry. All right, here we go. Ben Grun says, hey, Startalk. This is God, here to bestow upon you the keys of limitless energy.
Ooh.
What do you do?
Oh. Wow. Well, first, I don't think it requires God. We just have to tap the energy from the sun.
There you go. Bro, we got this. Thanks.
I say, God, we got, We'll worry about somebody else. Take care of that homeless man in the street. We got the energy thing. We're kind of slow on the go here, but the sun has basically unlimited energy. And the Chinese now want to put up a solar array in orbit, where there's no clouds. And if it's far enough away from Earth, it always sees the sun 24/7, beam it down to Earth by microwaves. So then you have this column of microwaves. What could go wrong?
Right. I don't want to cross that path for sure.
But unlimited energy. Yeah. Here's what I would do. You ready?
Go ahead.
I would do what they did in Iceland.
What's that?
Iceland is sitting on top of volcanoes. You know this?
Yeah.
Okay. So it's volcano land. It's not Iceland.
It's not Iceland, yeah.
Greenland is Iceland, not Greenland.
Right, exactly.
All right. It's the opposite here. So I want to do what they do in Iceland.
Go ahead.
They heat their water at these lava pits up in the mountains and then send the water into town, but they do it under the streets so that snow never accumulates.
Genius.
You don't need snow plows. Right. You don't need salt.
Right.
You don't need accident reports.
Nope. It snows and then the streets are they're just clear.
I would run hot water under everything. And then you just snow be damned.
It's radiant heating for your whole city.
Yes.
Wow, that's cool.
Yes, and other things I might use unlimited energy for.
I'll tell you what I'd use it for. Pretty much shutting down every war that's ever been fought. Because most of these wars that we fight are over some form of energy,
right.
And so it's just like, well, guess what? It's unlimited, guys. What are you fighting over?
Well, it could also be over food,
right.
or water supplies. There are other causes.
There are other scarcity resources.
Right. But I think we'd be smart enough.
But with unlimited energy, you would make water.
Today, nobody is going hungry because there's not enough food in the world.
Exactly.
If you're going hungry, it's because
some greedy bastard is keeping you from getting food.
Disrupting the food chain.
Exactly.
So I don't think that was predicted back in 1900.
No, right.
We saw the population growing exponentially. And we saw the food supplies growing linearly.
Yes.
And
there was a point where people thought that we would run out of food.
And just completely starve.
Right.
And so run out of food to feed everyone.
Right.
Rich
people are always going to eat now.
Right.
Exactly. Yeah.
Yeah.
Wow. So that's cool, man. I love the idea of radiant heating for your city, though.
Yeah. Just for this, just so you don't have to do it.
Yeah. Especially since we got 2 feet of snow. All right. I love that answer. All right. By the way, I think this is why Trump wants Greenland. What? Because he really thinks he wants Iceland. I think if you gave him Greenland, he'd be like, what is all this snow everywhere? I don't understand. I don't get it. There's so much ice here.
Plus, there are references to penguins there. There are no penguins in the north.
Yeah.
They're all there are no free penguins north of the equator.
Right, exactly.
They're all in captivity.
They're in captivity. Wow. Yeah. All right, this is Scott Oppenlander, or Oppenlander, not Open, Oppenlander. Mm-hmm. And he says, hey, Neil. Hey, Lord Nice. Scott Oppenlander here, tuning in from Phoenix, Arizona.
Which I'm told is a quarter mile from the surface of the sun. Yeah, Arizona. Yeah. I was in Phoenix one time.
Yeah.
For my first time.
Right.
And the sun came out.
Right.
And I said, oh, this is a beautiful day. The sun is out. No one is in the streets. No one is in the parks.
Yeah.
And when they walk in the streets, they walk on the side of the street that's shadowed.
Yeah.
And they only follow shadows around.
Hot. It gets hot.
Yeah.
Like,
whoa.
Yeah. Scottsdale. It's like night. The sun goes down and all the vampires come out. Where were you people all day? Anyway, since our universe appears to be a pancake shape, like planetary systems and galaxies, do galaxies orbit around some larger central structure, like an even more super mega massive black hole? Or are galaxy motions just more random or ununiformed? There you go.
Universe is not pancake shaped. So next question.
Well, there you have it. It's waffle shaped.
No, but to the point, galaxy motions are mostly random. And what I mean by random is they're not coordinated in some big way unless you're part of a galaxy cluster.
Okay.
And then there's some ballet of movement. However, some structures in the universe are so large that the average speed of the galaxy moving among other galaxies in that cluster is insufficient for the galaxy to have made one complete loop through that cluster.
Okay.
So that has significant consequences to what's going on there. It's not virialized. A virialized cluster is a cluster that has a very mature shape, where, like a beehive, all the galaxies are moving around. You step back, it has a spherical kind of envelope that contains them.
Gotcha.
But if it's kind of ratty, like that, it's not yet virialized. It comes from what's called the virial theorem, which talks about how energy can be shared from objects with high energy to objects with lower energy, so that everybody has approximately the same energy at the end of the of the process.
Very cool.
So virialization is the sharing of that energy.
Sharing of the energy.
So it drops the energy of the high energy objects. It could be thermal energy. It could just be orbital energy. And the lower energies come up. So, but it's a whole branch of physics. We talk about virialization of
galaxies.
Of matter in
matter
whatever
in
situation.
Okay.
So the ratty-looking galaxy clusters tend to not have been virialized.
Gotcha.
And so, yeah.
All right. So,
and by the way, we moving around the center of our galaxy takes about 200 million years.
200 million years.
That's much smaller than the age of the galaxy, which is 13 billion.
13 billion years, right.
Yeah, so galaxy is a mature shape.
And we're in a spiral galaxy.
Correct,
so
correct.
That's very cool, man. Good question. This is MX self-destruct. Okay. MX.
Is that a
That's what it says
here. Is that a thing here? Okay.
MX self-destruct, I have no idea. But his name is Seamus, and he says...
Seamus?
Yeah, he says, Dr. Tyson, Lord Nice, Seamus here from Los Angeles. We know that gravity is the result of the way space-time curves. So wouldn't it be more likely that gravity is simply a side effect of this curvature rather than a force with a carrier particle like a strong, weak, or an electromagnetic force? If there is a carrier particle, why is it not just the Higgs boson, since that imparts mass, thus providing the curvature for the universe that we call gravity?
Wow.
People are doing some work, man. People are doing some thinking.
Man, so I can answer 80% of that question.
All right.
It's an assumption that gravitation as a force in the universe has a force carrying particle.
Right.
And the assumption is that if you represented classical gravity, even Einsteinian gravity, with quantum physics, it would have to have a particle. So we even named this hypothetical particle.
Okay. The graviton.
The graviton.
Right.
Exactly. So the hunt for the graviton is on.
Right.
All right. And so the effect of the graviton and mass and energy is to curve the fabric of space and time, forcing you to move in certain ways that would not otherwise be the case if that were not occupying that space.
Right.
John Archibald Wheeler, a great physicist of the 20th century. In fact, I had him as a professor in graduate school.
Wow.
Okay. In fact, I met my wife in relativity class that he was teaching.
Cool.
I was sitting in the back row. She was in the front row.
And then you guys made relatives.
What I can't quite wrap my head around is if gravity is just the curvature of space and time, maybe it's not a force.
Okay.
Because forces have these carrier particles.
Right.
And if you're just falling along a curvature of space and time, what does it even mean to think of that as a force?
As a force. Right.
Right. So maybe it sits outside of the quantum paradigms that would require that there be a graviton.
Boy, that's something, that's kind of cool, man, in a way, because that means that there would be something in between the quantum.
An understanding that we don't yet have.
An understanding we don't have.
Right. It's a frontier.
Yeah, that's cool.
For sure. All right.
Well, there you go, buddy. I mean, listen, now you did some good. That's a great question. This is John Mayer. I think it's Meyer or Meyer. He says M-E-I-E-R. Meyer.
Meyer.
Yeah, John Meyer. Salutations from John in Carlsbad, California.
Carlsbad, California.
Yeah, Carlsbad, California. He says, Dr. Tyson, Lord Nice, the great defenders of art curiosity. I have a question that has plagued me.
Plagued that's a T-shirt if there ever was one.
Yeah, the great
Startalk, the defenders of curiosity.
He says, as budgets seem to be one of the significant components of innovation in science.
Yes. It's not a component of whether or not something is found to be true. It's a component of whether or not the research is conducted at all.
Exactly. He says, if we were to greatly increase the national or hypothetically the global science budget for building telescopes, what would you propose to maximize mankind's current technological possibilities, and what could they deliver in order to create the most powerful telescope possible? What would it look like? What would you point it at, and what might we see?
I would put an entire array of telescopes on the far side of the moon.
Right.
There's no atmosphere, so there's no clouds or anything. So there's no value to be on a mountaintop. You don't even have there's no value to being in an orbit.
Right.
The whole point of the orbit is you're outside the atmosphere.
Exactly.
On the moon, there's no atmosphere. You're good. You're good to go. So I put them all on the far side of the moon. And it doesn't even have to look towards Earth, where we have all of this contaminating radio wave noise and everything. I mean, Earth is just this messy thing in space.
It's terrible. That's a great idea, though. Put it on the far side of the moon, though, to watch put all the telescopes there.
Yeah, and then you put of all bandwidths.
Right.
You put all the telescopes of all the windows of the electromagnetic spectrum.
Right.
The radio waves.
Yeah, everything.
Everything.
And now what would you like to see?
I'm ready for the next generation of telescope that can see gravitational waves and neutrinos.
Wow.
That is not electromagnetic.
Not electromagnetic.
Yeah,
that would be fantastic.
I know.
Look at that.
Yeah.
Hey, great question, John Meyer. Way to go. All right, this is Tuomas Limata. Okay. Tuomas Limata.
How do you spell it?
Okay. TUOMASLIIMATTA. Laimata. Tuomas Laimata. There you go. I'm going to say that.
All right.
And he says, hey, it's Tuomas from Oulu, Finland. Long-time lurker and first-time Patreoner.
Long-time lurker?
Lurker, yeah. So he's been watching forever, but he decided
you lurk. You just look over the shoulder.
Now he pulled the trigger, and now he's welcome aboard, my friend. He says, I have a small question that I've been pondering for a very long time. Is time permanent? Thank you. Wow.
I don't know. I mentioned John Archibald Wheeler a moment ago. He's famous for uttering the following sentence. Matter tells space how to curve. Space tells matter how to move.
Yeah.
And that motion is defined to make time look simple.
I love that. That's so great. Motion is defined to make time look simple.
That's right.
Look simple.
That's right.
Yeah.
So it's time.
So without that, who knows?
Yeah. I mean, I want to believe that your whole timeline is just there and you're occupying this point in the present.
On the arrow.
That's correct.
Right.
That's correct. I want to think that, and I can sort of do it because I can lay out what's going to happen. That's what a schedule is. What's your schedule? You're
right.
I'm going to be here on Thursday and there on Friday and there on Saturday. And that's your future history. I don't know how you would live outside of a timeline.
Right. Yeah. Yeah.
Because where there is no time reckoning, then nothing moves.
Exactly.
Because then you can measure time by that. Otherwise.
Right. Otherwise, yeah. So that'd be kind of cool, though. I mean, no, it wouldn't be. I hate that idea.
To be outside of time?
Be outside of time. I hate the idea. However, that's what many people think eternity in the afterlife is that it's in a dimension that exists outside of time. And that's why it's eternity, because time does not exist. You know,
right. I see.
Yeah.
Okay. That's the reasoning given.
That's the reason given. You know. So you know. Anyway, that's very cool, man. What a great thing to think about.
And by the way, if that's the case, if you're outside of time, then that's the realm of divinity, the realm of spiritual, these sorts of things. I just don't know how a material object could be.
Could actually be there.
Correct.
Right. No. Yeah. That's the whole idea. History allows us to remember our future. So.
Nice.
Yeah. Anyway, Gavin Bamber says this. Hello from North Vancouver. Please visit and please tell me, how much does the universe weigh?
In fact, I'm going to be in Vancouver giving a public talk. May 4th.
May the 4th be with you.
Yes.
May the Neil be with you, Vancouver. How much does the universe weigh?
So you can do that on the back of an envelope.
On the back of an envelope.
Back of an envelope.
Sound like a big envelope. Must be a manila envelope at least.
So, yeah, we know the mass of the sun. We know the mass of all the planets. A fraction that of the sun.
Right.
We can practically ignore them because it's just in the round-off error.
Exactly.
Then we know how many stars there are in the galaxy.
Okay.
Then we know how many galaxies there are in the universe.
Okay.
Then we know, because we know where the edge of the observable universe is.
Right. Exactly.
We know these numbers.
Okay.
All you have to do is multiply it up.
Right.
Okay. So the sun is 2 times 10 to the 33 grams times, let's say 100 billion stars in the galaxy. So 2 times 10 to the 33 times 10 to the 11th.
Mm-hmm.
That's 100 billion. So that's 2 times 10 to the 43rd grams times possibly a trillion galaxies. That's
right.
To the 12th power. So that's
fuck ton.
That is the biggest unit of measure there is.
That's right. You can't get bigger than that.
I told you, I created
That's where
this.
I got it from.
That's what you got it from.
Yeah.
It's the vulgar metric system.
Yeah. That's where I got it from. That's why I said it. So,
because it's like, it's a, isn't there like an ass load of something?
There's a shitload.
A shitload. No, ass load is less than that.
Right.
Take this ass load of thing, take it to the market. Okay. We got more than that? That's a shitload. And then, yeah. So it's online somewhere. I think I had it at a Facebook post, but then I kind of hid it.
Yeah.
But it's out there.
I know. I just remember from that we.
And when I did that, someone wrote in and said, "This is beneath you."
Yeah, of course.
This is.
Listen.
Then I said, well, I've been hanging around Chuck.
I was going to say, just blame me because I get that letter every day. You bring down Dr. Tyson.
Okay.
Why does he sully himself being around you, Chuck? Like so many. So you'd be surprised. Like this guy.
You know what's interesting?
Wait, this guy wrote me. He went, "I'm sorry. I got to say this because it's so funny." He goes, "Hey man, no disrespect, but I hate you." And he's just like, "Please shut up. Please just sit there and don't say anything." Right? And then he's like, let Dr. Tyson give his talk. Right? And I'm just like, bro, that's not the show. What you're talking about is his lectures. If you want that, go watch a lecture.
Yeah.
But anyway, it just tickles me, when people there's a contingency out there that feels like I sully you.
I mean no disrespect.
Get your head out of your ass. But I hate you. Oh, it's so great.
So that's how you measure the mass.
That's how you measure the mass.
You just multiply it all
we
up.
got the numbers. And
sorry. I left out.
Go ahead.
Okay. There's 6 times as much gravity in the universe as is what is created by that mass that I just calculated.
Right.
So if that extra gravity comes from matter, then we legitimately are calling it dark matter. So you take whatever number you multiplied up, multiply by 6.
That's phenomenal.
Right. And we can do that without going out there with a scale.
Right. Yeah.
There are ways to do this.
Yeah.
Didn't we have an explainer? Was it an explainer or question? But we weighed a truck.
Yes. Yeah, we did that. And basically it was about using the air tires in the truck and all that kind of stuff. Anyway, let's move on because we're getting derailed.
Time for just a couple more.
All right. This is Mile from Macedonia. She says, "Hey, Chuck. Hey, Neil. Mile from Macedonia, Balkan, Europe, world. Japanese astrophysicists have identified a strong gamma ray glow near the Milky Way's center, matching predictions for annihilating dark matter particles, WIMPs." Okay?
Weakly interacting massive particles. They're called WIMPs.
WIMPs. Could you explain how these particles are different from regular matter?
No.
There you go.
I'm sorry.
That's so great.
The hunt for dark matter.
Right.
It's who was doing that was Katie Freese.
Right.
We've had her as guest.
Yes.
You go dig up Katie Freese.
Yeah. Watch that. That's actually a really fascinating episode that we had.
Yeah. Freese. Freese.
Yes.
She's an expert on dark matter detection. She's a theorist.
She's a theorist.
So she would think about what particle would interact with a dark matter particle for that to happen. Right. Now, I'd be surprised if dark matter interacted with such ferocity that it would be giving us gamma rays.
Right.
That's a little bit mysterious to me.
Right.
Because we would see that everywhere.
Right, exactly.
You'd think.
Yeah. exactly.
You can't take this one example in our own Milky Way and say, see? When you have a trillion other galaxies.
Right.
That should be a common phenomenon.
It should show up someplace.
Our sample size is so large, you can see even rare phenomenon every night.
Boom, that's awesome.
Yes.
I love that. All right.
A quick reference to medicine. If I have a new a pill, a new cure for something, and it's medicine that you take, it's not safe for. This is an old saying in the field. It's not safe for anyone until everyone has tested it.
Exactly.
Think about that.
No.
You can test on 1,000 people, but if you have a condition that's 1 in a million, it's not likely that you were in that data set.
That you weren't in that sample.
You're not in that sample,
exactly.
right?
Yeah.
So ideally, you would test on everyone.
Right.
They know exactly for whom it works and who it doesn't. That's not realistic.
It isn't realistic. And
whereas the universe is big enough so that extremely rare things happen all the time. Yeah.
Right. T-Mobile 5G home internet has some big news you should know about. They now have the fastest 5G home internet according to the experts at Ookla Speed Test. Now, in practical terms, it means photo backups happen faster, streaming a documentary doesn't stall halfway through, the physics of waiting reduced. What's also notable is that this jump in speed doesn't come with added complexity. Setup is simple. You plug it in and you're online in less than 15 minutes. And the value side of the equation holds up too, with a plan price that's backed by a 5-year price guarantee. So, if you want the fastest 5G home internet with a simple setup and savings that stick, get T-Mobile 5G home internet. Just visit t-mobile.com/home internet to check availability today. Price guarantee, exclusions like taxes and fees apply. Fastest based on Ookla Speed Test intelligence data, second half 2025. All rights reserved.
Last question, Chuck. That's all we have time for.
All right. Let's go with Larry McGuire, who says, hey, Dr. Tyson.
Jerry McGuire?
Show me the question. This is
Show me the question.
This is Larry McGuire. He says, hey, Dr. Tyson, Lord Nice. Larry from Caledon, British Columbia, just down the road from the Dominion Astrophysical Observatory.
I use software that they wrote.
Oh, really?
Well, there was a important colleague of mine from that observatory who wrote data reduction software.
All right.
And it was the primary software I used for my thesis, which is sitting right there, that big old fat book down there.
That one right there.
Yeah, yeah.
So he says, I'm curious about your tools to keep looking up. What was your first telescope? And do you still have a telescope? And what type is it?
Okay, very good. Thank you. That's a great question to end on.
All right.
So my first encounter with the night sky was this dome of the Hayden Planetarium.
Oh, that's so cool.
Because I grew up in the Bronx.
Right.
There's no night sky to New Yorkers. We had no relationship.
Right.
And so that was my first night sky.
Okay.
Then a friend of mine, my best friend growing up, he was smarter than me in like many countable ways.
Okay.
Right? He taught me chess. He taught me poker. He taught me gambling. He taught me.
Wow, that doesn't sound like a good friend. I'm just saying that's how people feel about me hanging around you. He was your Chuck Nice. Like, he was just like, all right, let me show you how to gamble.
Yeah, all his grades were higher than mine and everything. Right. So, in fact, I'll give his name. His name is Philip Branford.
Branford.
And when I was on Celebrity Jeopardy, I pointed him out in the audience.
Oh, really?
He came to the show. Came to the show. I pointed him out, and I say, he first got me to watch Jeopardy.
He first got me to watch Jeopardy, and first dude to give me drugs. What was your first telescope?
Okay, so he had a pair of binoculars.
Oh, cool.
And so I looked through the binoculars, and I never knew. We weren't wealthy enough to have like binoculars just laying around. Yeah. That's a different, that's
a whole
other, when you got that.
That's an income level
exactly.
thing.
That's an income, just a level.
Just a level.
Laying around the house.
Exactly.
Get the binoculars when we go to the.
Abner! Look at what they're doing over there, Abner!
Where'd you get Abner?
I don't know. Anyway.
Okay. So he invited me to look up with them, and I saw the moon. And the moon wasn't just bigger.
Yeah.
It was better.
Yeah.
It was, oh my gosh.
Right.
And you don't want to look at a full moon because that sucks.
Yeah.
You want to look like a half moon.
blown out.
Yeah. Any photographer knows you don't directly illuminate something.
Right.
There are no shadows. There's no depth. Right. You wait for there to be shadows. Any other phase, ideally half moon, which is officially called the first quarter or last quarter, first or third quarter moons. So, longest shadows visible. I'm looking at it with the binoculars. It was like, whoa, this is like a whole other thing.
Nice.
Oh my God, I felt like I was there.
Nice.
Yeah. So that was like, tipped me off that stuff was going on up there that the human eye does not notice.
Right.
So then.
That was your gateway.
This. Yes, the binoculars were the gateway drug.
That was your gateway drug.
Curiosities.
Cosmic curiosity.
Then when I'm 11.
Okay.
We moved to Lexington, Massachusetts.
Okay.
We spent just a year there. My father had an academic appointment.
Okay.
And for just 1 year in the Kennedy School of Government.
All right.
Yeah, now it's just called
now it's called the Trump Kennedy School of Government. But no one wants to perform there.
But you're talking about the Kennedy Center? Right.
Yeah.
Okay. I'm a city kid and we're living in a private house. Like, what's up with that?
Right.
You want me to do what with this shovel? You want me to do what with this rake?
Right.
Oh, isn't the snow pretty?
Right.
And then they hand me a shovel.
Of course.
Right. It's like, what?
Yeah.
Okay. And then it's autumn and the leaves are on the ground. What?
Yeah.
The grass gets long. Okay. What? Mow? What?
Yeah.
I'm a city kid.
Yeah. You're pining for the city again.
We just stayed. It was someone else's private home for a year.
Right.
That's what it was.
Yeah.
And they were on sabbatical or something. Anyway, my interest in the universe was stoked because I learned that Harvard had a Center for Astrophysics.
Interesting.
Whole department of it was like, whoa, that's like really cool. And so my parents saw this and they took me there for one of their open house nights. They had telescopes.
Wow.
I went in there and it was like, I died and went to heaven. And I'm 11 years old. Wow. Okay. For my birthday in October that year when I turned 12, they bought me my first telescope. It was a 2.4-inch refracting telescope. That telescope I rapidly outgrew. But I mean, I saw the rings of Saturn, the weather bands on Jupiter, Jupiter's moons, nebulae, the Andromeda galaxy, the sunspots. I had special filters for that. And then I'm like 12, and my parents just let me out there to observe the sun. They'd never even asked. I think
that's cool, man.
They just trusted that I knew what the hell I was doing.
Well, no kid walks out with a telescope to go get in trouble. Hey guys, I'll be right back. Gonna go rob a bank with this telescope. No. I'm just, in retrospect, they would never concern that I did not know what I was doing. Right.
I'm not kind of angry.
Well, listen. Yeah. I mean, you're not going to question your kid when they're just like, I want to go look at the sky.
Yeah, with a telescope.
With a telescope.
Okay. Yeah. So, and then when it did snow, this is New England, right? So there's a lot of snow there. Yeah. I want to take the telescope out back. And winter nights are long.
Right.
Anywhere they're long. And the air is crisp. There's much less humidity.
Right.
And so the really good some of the best observing is in very cold nights. So I dug a path into the middle of our we had a backyard and a little circle. And that was my little observatory circle. And I would take the telescope out there. And I had several eyepieces, and that's what I did.
That's very cool.
Okay,
man.
So within a year, I outgrew the telescope.
Okay. Tired of looking at this same stuff.
No, so we sold it to a friend, or acquaintance, and then I would then buy my own telescope the next year.
Gotcha.
When I was 13, no, maybe a year and a half later, I would buy my own telescope with money I earned by walking dogs. And that was a 6-inch Newtonian optics reflecting telescope.
Well, okay.
It's a 6-inch telescope.
Nice.
That telescope I took to Africa to view a total solar eclipse when I was 14. And I lied and told everyone I was 15 because
because that made a difference.
Because I wanted the respect of a 16-year-old. I went alone on this cruise. It was like a science expedition to the.
Very nice.
So I took my telescope with a big old. The telescope is huge and a big old crate. That telescope has since been gifted to a museum of science in Kentucky, who decided to make an exhibit of famous people's first telescopes.
Interesting.
They have my telescope.
They have your telescope.
Yeah, it's like on permanent loan.
That's great.
I haven't visited there. I don't know if it's on display or anything.
Right.
They got my telescope.
That's cool, man.
And I also took it to the Mojave Desert, where I was in astronomy, lived nocturnally in an astronomy camp.
Very nice.
Talk about geeking out.
Yeah, man.
Who else is going to be there but like crazy other
geeks. That's it. That's fun.
Yeah, there were girl geeks and boy geeks, and we were all there. And since then, I went a long period without a telescope when I went to college, and I said, "Time, I got to get back in the game here." Much later, when I had some cash, then I bought a very high quality optical telescope, and since then I have 2 digital telescopes. Yeah, which takes some of the fun out. You know, you just set it. You just set up the tripod. Go back into your
It's
warm.
the Ron Popeil of telescopes. Set it and forget it. Yeah.
You go back in to your warm living room, and you just guide it with your iPad.
Love it.
So I'm old school. Make it hard for me.
Love that. Love it.
So so at the time I was a member of the Amateur Astronomers Club, which had monthly meetings here at the American Museum of Natural History, under the shadow of the Hayden Planetarium. So I go way back in this.
Nice. There
That's
you go.
what it is. Well, those are my telescopes.
Very nice.
And in this office, I have a 2.4-inch refracting telescope, which is not my original, but it's exactly the same size. Okay. And in the hallway of the astrophysics department, there's a 6-inch Newtonian reflecting telescope, which is exactly the size of my telescope. But they were selling them in the shop 50 years ago.
Wow.
And this one was the display model, and we just kept it. Now that the shop is all blended with the other shops.
Very nice.
And so those are my 2 No, you were the first to no one in the department knows this.
Right.
That I had that telescope there and this telescope there, that same optics. And so when I see them, I feel a little nostalgic.
A little nostalgic.
Yeah, except for when I was on the roof with my telescope.
Right.
And then neighbors call the cops.
Oh, well, yeah. Because, you can't have a black man on the roof.
With something that looks like a bazooka.
Looks like a bazooka. I think he's going to murder the president. I'm not sure. He's up there with a big scope.
Yeah. Anyway. This cop approaches me, hand over his gun. It's like, what the hell? I'm a 15-year-old kid.
That's funny.
Just absorbing the universe.
Nice.
One last thing, and then we got to call it quits here.
Okay.
So there's some children's books that tell my story growing up.
Okay.
And one of them retells that story of me on the roof.
On the roof?
And they show the cops showing up. But then the cops show up and I say, have you ever seen Saturn through a telescope before?
Right.
And then they're enchanted. They're on. But up until that moment, it's actually quite tense.
Of course.
But they don't know what I'm telling them to look at. And
You got them with Saturn.
You got to have the moon or Saturn ready to.
That's a good one to get anybody.
And that children's book, which showed the cop, was banned in Pennsylvania.
Oh, no.
Yeah.
For what?
Because it was showing
a police officer in a bad light?
Yes.
Oh,
do you remember there was a period of book banning?
Right.
That wanted to protect the image.
Right.
Yeah. And so, and I tracked it, and it was only on the ban list for about 6 months, 6 to 8 months.
Those people who ban those books, they would like the version where the cops show up and they go, "Oh, well, hello, young Negro," and then they go, "We'd like to introduce you to somebody," and then all of a sudden they bring out Carl Sagan, and you're like, "Oh my God!" And then everybody lives happily.
It's not how that one went down.
Exactly
right. All right, so that's my story of my telescope.
Oh, well, that was cool.
Thank you for that question. Yeah, very good.
All right,
we got to call it quits there.
Well, there you have it.
That was as potpourri a selection of questions as there ever was.
That's why they're fun.
There you go. Chuck, always good to have you, man.
Always a pleasure.
Neil deGrasse Tyson for Startalk Cosmic Queries. Until next time, keep looking up, with or without a telescope.